Hey guys, we're going to do two things today. Number one, we're going to derive a formula that relates the period of oscillation of a spring mass system with the mass and the spring constant of your spring mass system. And then we're going to do some problems involving that formula. And then I'm going to give you the introduction to the lab you're going to do tomorrow. That way you can walk into the class and just immediately start doing the lab. Does that make sense to you guys? Yeah. Good. Thank you for saying yes, whoever said that. Here we go. First, let's derive our relationship between the period of oscillation, the mass, and the spring constant of a spring mass system. What formula do you suppose I'm going to start with? It's my favorite formula. It's the one that's most of my derivations start with. Anyone thinking F equals ma? Thank you very much. So we got F equals ma. On this mass, the force on the mass is spring force. So I'm going to go a negative kx equals ma. You guys okay with that? I have to do negative kx because the x is in the opposite direction of the acceleration. Next, we have a relationship with x and a, correct? X we found yesterday is a cosine of omega t, or not yesterday, the day before, I don't know. Whenever I did all that circle stuff, that was yesterday, right?
Yeah.
Wow, seems like forever ago. And those of you in calculus know that when you take the derivative, you get negative 8 omega sine of omega t, and when you take the second derivative, you get negative a omega squared cosine of omega t. And now that I have these expressions for x and a, I'm just going to plug them in. Negative k times a cosine of omega t equals m times negative a omega squared cosine of omega t. What's the first thing you notice cancels? What? Good, the cosine of omega t's cancel. What else cancels? Thank you very much, Fatima. The a's, In fact, do you notice period doesn't depend on amplitude? What they're essentially saying is, look at the small amplitudes, and maybe I should use a heavier mass here. Just a second. Okay. Look at the small amplitudes of oscillation there. You see the small amplitude of oscillation? What if I make it oscillate at a much greater amplitude? Is that period going to be any different than the period of oscillation when I gave it small amplitudes of oscillation?
No.
And the answer is no. No way. That's the weird thing about spring mass systems. You get the same period no matter what the amplitude of oscillation is. So the fact is, when you do your lab tomorrow, I don't care how wild you have this thing going up and down, doesn't matter, because period is independent of amplitude. Great. Now, of course, tell me, where is it traveling faster, like speed, meters per second? In which scenario is my mass traveling faster? The scenario with a large amplitude of oscillation, or the scenario with a very small amplitude of oscillation?
The large one?
Yeah, the large one, right? Because you know that V max is equal to A omega. And so, yeah, I mean, the bigger amplitude, you're going to get a bigger V max, right? But the fact is, the period is not affected by amplitude. Notice one other thing that cancels, the negative signs. And so I end up with k equals m omega squared. Or I can solve for omega, and I get omega squared equals k over m, or omega equals the square root of k over m. Okay? This is the formula I personally prefer, but your textbook and the AP exam don't. In fact, the formula on the AP exam is not that one. The formula they give you on the AP exam is this one. So I need to show you where that one comes from, even though me personally, I'm in love with this one, because it's so simple, you know? Are you guys okay that omega is equal to 2 pi times your normal frequency?
Yeah.
So I'm going to substitute 2 pi f in for omega. So I get 2 pi f equals radical k over m, or f equals 1 over 2 pi times radical k over m. That's my formula for frequency. If someone gives me spring constant and mass, that's frequency. But we also know that frequency is equal to 1 over the period, correct? So I can stick 1 over the period in for frequency, and I get 1 over period equals 1 over 2 pi times the square root of k over m. And now I'm just going to flip every fraction. And I get period equals 2 pi times the square root of m over k. You guys okay with that? That's where it comes from. That's the formula. Learn it, live it, love it. You ready to do a problem? Good. I saw some expressions of yesness. So here we go. Do you remember yesterday? I had a 1 kilogram mass on that spring, and it ended up doing 5 cycles in 6.6 seconds. Do you remember that from yesterday?
Yeah.
Then what I would like you to do now is please find the spring constant of the spring. Find K. I'll give you a hint. You're going to have to use this formula, which means you're going to have to get the period. You know the mass. Just plug it in and do your algebra. And if you guys are like my previous periods, about half of you will be able to do the problem. The other half will not be able to do the algebra. And that's okay. That doesn't make you any less worthy of love. Just because you can't do algebra. Is anyone having a difficulty? Does anyone need my guidance? What is that? Birds, maybe? My wife. I had a cat under my house yesterday. We have a basement, and the basement is, has screens in the vents, but one of the screens is gone. So some cat in the neighborhood got under our house. So I was in my son's room, and I'm hearing meow, meow, meow. And it's like, where's that coming from? It was coming from under the house. Little key. All right.
Cute little kitty.
So what'd you guys get for spin constant? Someone tell me.
0.23.
Say again?
0.23.
0.23. Unfortunately, that's wrong. Did you try to punch this in your calculator?
Is it a big number?
Wait.
Like,
Well, 20 something.
oh, I got 22.6.
Oh, 22.7 or 22.6?
7.
Okay, how many people got 22.7? Yay for all of you people who are good at math. That was about, let the record show, is about a third of the class. 22.7. Anyone who got it wrong, are you able to see why you got it wrong? What went wrong with your math? Maybe you're not doing the punchy good? I don't know what to tell you. When you're dividing by 4 pi squared, maybe divide by 4 and also divide by pi squared? Yes. Sure. And Chris, that's probably what happened to you. Yeah. You got to divide by 4 and by pi. Yes?
I did t divided by 2 pi and then I squared it. That's why I got 0.2.
Well, I'm sorry to hear that. What you need to do, if you do, 1.32 divided by 2 pi, are you aware that your calculator thinks you're multiplying by pi, not dividing by pi? So you either need to put this in parentheses or you need to do this. One of the two. But you can't just put 1.32 divided by 2 pi. That's bad. Calculator will think it's 1.32 divided by pi, 2 multiplied by pi, not divided by pi. Alrighty, and by the way, what's the units of this? Is it newtons per meter or newtons per centimeter? Well, I'll tell you, whenever you use this formula, it's always got to be newtons per meter. Because this is all MKS, this is all meters, kilograms, and seconds. Like, look at this. Are you guys see that the units right now are kilograms per second squared? Do you see that's the units of my K? And so I need to get it into newtons, correct? So I'm going to multiply top and bottom of this fraction by meters. And now do you see that kilogram meters per second squared? That's my newtons, and I'm left with meters. If you use this formula, you will never plug in with newtons per centimeter, and you will never get an answer with newtons per centimeter. It's always got to be MKS. It's always got to be newtons and meters, kilograms and seconds. So this ends up being newtons per meter. Okay? You guys good on that? Okay, then here's the next question. I am now going to put a ½ kilogram on that same spring. This is the spring I was dealing with yesterday. I'd like everyone to please predict what the period of oscillation of this mass is. Now, put 0.5 kilograms mass on your 22.7 newtons per meter spring. Get the period. Please find me the period of oscillation. Predict the period of oscillation. Then we'll actually do it. And boy, will we be shocked when there's, agreement. So does everyone know what to do? ½ kilogram, 22.7 newtons per meter. Get me the period. Yes, no. I'm keeping my eye out at Vons. When they put the Chex Mix on sale for $1 a piece, I'm going to get like 10 of them. And then you can have them. So what are you guys getting for your tea?
0.9.
What's that?
0.9.
How about to 2 sig figs?
0.93.
Good enough. You guys okay? 0.93. Okay. So we are going to now do a experiment. Let's go ahead and put this into oscillation, and I'm going to find what the period is. Now yesterday I took 5 periods. How many periods do you suppose I'm going to do today so I can be more accurate?
10.
10 is good. Yeah, you might have thought 100 or 1,000,000, but no, just 10. Okay, and I want to remind you, when you clicky, that's a 0, correct? The most common mistake students make is they think they're counting 10 periods, but they're actually counting 9 because the thing's going up and down, and then they go clicky. 2. You know, it's like, wait, you know, they start with 1 when they go clicky, so they'll go clicky 1, 2, but don't do that, start with 0. So it's like clicky 1. Okay, you guys ready? Here we go. Okay, come on, baby. Gotta get the rhythm of it. Here comes clicky 1, 2, 3, 4, 5, 6, 7, 8, 9, clicky. So I got 9.42 seconds. 9.42 seconds. Wait, am I off by a factor of 10?
No.
What do I have to do?
Divide by 10.
Oh, divide by 10, because there's 10 cycles. Right, so don't make that mistake either. So I get 0.94 approximately seconds. So tell me, was my prediction pretty accurate?
Yeah.
Heck yeah, 1% off. I'll take 1% off on the lab where I'm going clicky. Okay, great. So that's it. That's the formula. Now it's time to talk about your lab.
Should I keep on filming or not?
Oh, good question. Maybe so in case someone's absent and so they're not going to get the lab. So yeah, no, I don't know. Yeah, keep filming. We better keep filming. Okay. Let me tell you what the goal of the lab is. How much time we have left? Oh, lots of time. Intro to lab. Okay. Here's my, okay. The goal of this lab is to find a spring constant by measuring mass and a period. Find the spring constant, K, by measuring mass and period. That's your goal. Now, your first inclination would be to say, well, that's easy, Mr. Shana. I can just choose one period and one mass and plug into the formula and get K easy as you please. But this will not prepare you for the AP exam. And there's a type of problem that the AP exam people absolutely love, but that problem has not shown up on the Physics 1 exam for the last 3 years. And so I'm thinking for sure they're going to put a problem like this on the Physics 1 exam this coming May. So I need to make sure you guys are awesome at this type of problem. And I'll tell you the type of problem is you're going to graph your data in such a way that you get a straight line, and then by using the slope of the straight line, you'll be able to find what the spring constant K is. That's the sort of thing they're going to want you to do. Here's what I'm talking about. Remember I said measuring mass and period? So I'm going to want you to take a bunch of mass versus period measurements. That is, for a particular spring, you'll hang a mass on and get the period, then hang a second mass and get the period, third mass, fourth, fifth mass and get the period. And so now you'll have a table of data, 5 masses and 5 periods. That's what you're going to do to start. Next, we've got an equation, T equals 2 pi times the square root of m over k, which means period equals 2 pi over the square root of k times the square root of m. Now let me ask you, what if I were to graph this data here? What if I were to graph m, which is in kilograms, versus period, which is in seconds? What should the graph look like, given that this is the formula? What should the graph look like of if I graph t versus m and the formula is t equals a bunch of stuff times the square root of m? Should it look like a straight line? No, what should it look like?
Parabola?
What's that?
Parabola?
Okay, a parabola, but actually a sideways parabola. It should look like what Chris is motioning, where if I'm not on the camera, Chris is going like this, because it's going to look like a radical, right? You're going to graph your data, and the data is going to look like a radical. You know, it's going to look like that if I graph t versus m. But I'm not going to graph t versus m. No way, man. I'm going to graph t versus the square root of m. And so the units is going to be the square root of kilograms here, and the units of this is going to be seconds. What am I going to get if I graph t versus the square root of m? What should I get now? What's that? Okay. What do you think? I'll tell you what, it's not going to be this anymore. What's that?
Linear?
Thank you, Chris. Wow, you're really on fire on this stuff. Yeah, linear. It's going to be a line, right? Because if I double radical m, I double t. If I triple radical m, which means I'd have to multiply m by 9, then I triple t. Or if I double radical m, which means I'm quadrupling m, but we don't care about that. If I double radical m, I double t. They're proportional to each other. T is proportional to radical m. And so, yeah, if I graph t versus radical m, I'm going to get a straight line. You see that? And so that's what I'm going to need you to do. Once you get this table of values, I'm going to need you to get a third column, which is the square root of m, and then you're going to graph t versus radical m. Graph t versus radical m. And you tell me, what's the slope of that line going to be equal to? What's the slope? If I graph t versus radical m, what's the slope of the line going to have to be equal to? Someone raise your hand so I know who to call on. Yes?
2 pi over rad k.
Yeah, 2 pi over rad k. You guys okay with that? Slope is 2 pi over rad k. Okay? And so once you get the slope, you can get k. Get the slope, get k. And that's what I'm going to ask you to do. You're going to do this for 3 scenarios. Do this for 3 scenarios. Number 1, a single spring. Number 2, you'll get a second identical spring and put them in parallel of that single spring. And then the third scenario is going to be 2 springs, these same 2 identical springs in series, which means they're connected end to end. That's what I mean by them being in series connected end to end. And so one of the outcomes of this lab should be that whatever the spring constant is, what spring constant should you get if you put 2 of these springs in parallel? What should it do to the spring constant when you put them in parallel? What do you do to the spring constant when you put 2 identical springs in parallel? Well, you got 2 choices, cutting it in half or doubling it. How many people say, when I put 2 springs in parallel, I cut the spring constant in half, which means it's now looser? Okay, how many people say I double the spring constant because it's stiffer? Yeah, well, those of you who say double, you're right, and you're gonna discover it. Even if you don't believe it, you'll discover it tomorrow. This should be twice the spring constant. And tell me, when I put 2 of those identical springs in series, so I'm essentially doubling the length of the spring, what should I do to the spring constant now?
You have
Yeah, cut it in half. And you're going to experience that tomorrow. So even if you don't get it yet, you'll experience it tomorrow. So do you guys understand what you're doing? Get a bunch of versus then take the square root of that guy, and then graph period versus that guy. Make sure you make a nice graph. Give me the axes labeled with units. Draw your best fit line. Get the slope. Set it equal to 2 pi over rad k and solve for k. But now, I need to show you a different way to do it. I'm going to go to blue land. So everything I write now is going to be in blue. Here. Suppose you're the type of person who hates radicals. You just don't like square roots. Suppose you hate radicals. You don't want to graph t versus radical m because you hate radicals. So tell me, what would you do to both sides of this equation if you're the type of person who hates radicals?
Square 'em.
Yeah, good for you. Square it. So now you're going to have t squared equals 4 pi squared times m over k. Or I can write it t squared equals 4 pi squared over k times m. So now, to get your straight line, you're not going to graph t versus rad m. What are you going to graph now?
T squared.
Say again, Sean? Beautiful. You're going to graph t squared, which is in seconds squared, versus m, which is in kilograms. And yeah, you'll still get your straight line, right? You still get that straight line if you graph t squared versus m. So if you don't like radicals, then you're just going to have to get another column, t squared. Don't get rad m because you hate radicals. Just get a column with t squared and then graph t squared versus m. And you tell me, what's the slope of that best fit line? What's that going to be equal to? Say again, Sean?
4 pi squared.
Yeah, 4 pi squared over k, which I think is easier to solve for. So if you get the slope being like 0.01 or something, just multiply both sides by k, divide both sides by 0.01, and there's your answer. So I'm going to present to you, you can do it either way tomorrow. Don't do it both. Just choose one way. But you know, if you're okay with radicals, graph t versus rad m. If you hate radicals, graph t squared versus m. You'll get the same answer. It all works out just swell. Just remember, if you graph t squared versus m, you're going to have the slope of the line being 4 pi squared over k. Any questions or problems on this? Okay, and remember, you're going to do it for 3 scenarios. So right when you walk into the room, you're going to grab 2 identical springs, and then the rest of the lab, you'll work with those 2 springs. You'll do this for the single spring, do it for 2 of those 2 springs in parallel, do it for the 2 springs in series. Any questions or issues on any of this? Alrighty, then hey, I got nothing else to say. We're done. Bye-bye.